Hello everybody.
This is the paper back cover, and it is available in this price 689 currently. Hmm. So you can, if you want to buy this one, you can buy it online or offline, whatever you wish. Hmm. I need to follow this chapter 7, system of linear differential equations. Hmm. System of linear differential equations. Okay. Now, what is this system of linear differential equation? Firstly, let me define the linear differential equation, because in the differential in ordinary differential equation, we what is differential equation? We know that differential equation is actually an equation involving the involving a dependent variable. Over here, if you consider this kind of differential equation, say dy dx, hmm, dy dx, dy by dx, that is equal to maybe some function of x, f of x. Hmm. In that case, you see this quantity y, this would be a dependent variable, and this variable x, this would be the independent variable, and we may have higher order derivative, second derivative, third derivative, and so on. So over here, the differential equation is actually a relation involving a dependent variable, an independent variable, and their derivatives. Now, if a differential equation is written in this way, say some quantity, suppose a1 into y plus, let me write it over here, because over here the writing is a bit difficult for me. Hmm. Hopefully this is clear to you. Suppose we have y plus dy dx, or in brief, we can write it as y prime. Dy dx is equal to y prime. And suppose the coefficient of y is equal to, say, a0, that is a function of x, plus maybe a1, it may be a function of x, okay, and so on, plus maybe the second derivative a2, y double prime, etc. Hmm. For the time being, let's confine within y double prime is equal to maybe some function f of x. Okay. So what is this? Over here, you can observe that the dependent variable y and its derivative, the power of this all these quantities, dependent variable y and their derivative, the power of all these quantities are equal to 1. We can write it in this way: y to the power of 1. We can write it in this way: y prime to the power of 1, hmm, and maybe y double prime to the power of 1. So if a differential equation is written in such a manner that the dependent variable y and its derivatives have the power 1, in that case, this kind of differential equations are called linear differential equation. Okay, linear differential equation. Otherwise, the differential equation is called nonlinear. Okay. For example, suppose over here we have in place of this expression, suppose over here, suppose we have y prime whole square, maybe y double prime whole cube. And over here just you can treat as y. Alright. In that case, the power of y prime, y double prime is equal to 3. The power of y prime is equal to 2. We may also have this kind of expressions like suppose b1 maybe some function of x into y prime into y double prime. So we actually have the product of two derivatives. Hmm. We could also have maybe sine of y prime like this. So these are all examples of nonlinear differential equations. So in case of differential equation, we actually have mainly two categories of differential equation. One is the linear differential equation and another is the nonlinear differential equation. Hopefully this is clear, the difference between linear and nonlinear differential equation. কারোর কোনো question আছে related to these definitions? Anybody?
না স্যার,
Clear, sir.
Okay, so um, so let's continue. Now, what is simultaneous linear differential equation? One more thing regarding linear differential equation. Over here, these remember these coefficients are always functions of x, and most of the times we shall consider these functions as a constant quantities. All right, these functions, these coefficients a0, a1, a2. In most of the times, we shall consider these coefficients as constant quantities, not functions of x. It would make our study a little easier for us because whenever these coefficients are constant, uh, there is a definite technique for solving a linear ordinary differential equation. And if these coefficients are not, what should I say, if these coefficients are not constant, they are functions of x, then sometimes we are able to find the solution of this kind of differential equation, but most of the times we do not have any definite technique by which we can find the solution of the differential equation. That is a very challenging task in the solution of differential equation. Maybe the reason behind it is that we do not have sufficient class of functions by which we can express the solution of a differential equation. What I am trying to say is that, say, you see, whenever we make some solution of differential equation, what we do in solving a differential equation, we actually perform the integration process, isn't it? So in the integration process, you see, you already got this word probably LIATE. L stands for logarithmic function, I stands for inverse function, A stands for algebraic function, T stands for trigonometric function, and E stands for exponential functions. So there are some other category of functions as well. Some advanced definition of functions has been done in order to solve differential equations. But the problem is that with this limited number of limited category of functions, it is not possible to find the solution of the differential equation. That might be one of the most important problem. Or even if it is possible to find the solution of a differential equation, the solution process sometimes become very much laborious, that it is very hard to find the exact solution of the differential equation. And that's why we generally, most of the times in our research work or in our advanced field of application, we actually try to solve a differential equation by a particular technique that is called numerical analysis, numerical methods. You will learn different numerical techniques in your future semesters regarding the solution of differential equation. And this is all about ordinary differential equation. There is a special kind of derivative that is called partial derivative that you will encounter in future, and there is one separate branch of differential equation that is called partial differential equation. So there linear differential equation, non-linear differential equation, and several other category of differential equations are there, like semi-linear differential equation, quasi-linear differential equation, and all. So solution of this kind of differential equation is very challenging task. That's why whenever we try to solve this kind of differential equation, most of the times we generally fail to get a solution by applying this kind of limited category of functions. Hmm. So I'm not going to discuss about these advanced studies. Forget it. What I am trying to say is that there are other techniques that is also available in differential equation that you will encounter in your future semesters. And for the time being, as because it is an introductory course, sometimes we choose these coefficients as a constant quantities. And if these coefficients are chosen as a constant quantities, in such cases we call linear differential equation with constant coefficient. All right. So you will encounter this kind of differential equations in future. Linear differential equation with constant coefficients. Okay. Now let's continue our discussion with this what is called simultaneous linear differential equation. Simultaneous linear differential equation, or particularly as per the syllabus, it should be system of linear differential equations. What is this? System of linear differential equation. Linear system of linear differential equation. What is this? Over here, we consider we consider more than one differential equations simultaneously. Okay, and for simplicity, we call it this coefficient not as a0x. We simply call it a0. A0, it is understood that a0 would be a function of x. Okay, just for simplicity. So let me make this simple. So this kind of simple notation, because otherwise it becomes a bit cumbersome. Now over here, this variable x is taken as the independent variable, and y is taken as a dependent variable. All right. And along with this kind of functions, along with this kind of equation, we suppose there is one more equation, maybe the dependent variable may be z, hmm, like this. That may be another function. Over here, in case of a0, let us write it as b0. b0, this coefficients b1, then this coefficients b2, and maybe this is our f2, and maybe this is our f1. Okay, suppose we have two differential equations, and in these two differential equations we have this kind of expression. Over here y is the dependent variable, and over here z is the dependent variable. Only one independent variable x is there. Now it may so happen, this is a very simple expression. This is one example. Another example, you see, it may be a bit complicated. Say suppose in place of y we have z, and in place of z we have y. A little bit mixture. Maybe over here we have maybe z double prime. So this equation, this is actually, these are called coupled system of linear differential equation. Coupled means x and y are mixed. Hmm. Over in this example, the first equation was purely an equation involving a single dependent variable y, and this second is the equation involving a single dependent variable z. But if you look at this example over here, in this first equation, this is this is a differential equation, linear differential equation, no doubt, because the power is always equal to 1. The power of these dependent variables, z double prime to the power of 1, then y prime to the power of 1. But over here, what we have over here, this equation, the first equation and the second equations, both of these two equations are actually having two dependent variables. In the first equation, we have y and z as two dependent variables, and in the second equation as well, we have y and z as two dependent variables. So that is actually the most general case that may appear over here in case of system of linear differential equation. And in this system of linear differential equation, we shall use a notation that is called d operator. What is this d? D is the operator ddx, and in your book you will find that this is the operator ddt. Whatever it is, x or t, that would be the derivative operator with respect to the dependent variable. Hmm. So let's make it. Let's convert this dependent variable into t. Okay. Let us write it, the dependent variable, the independent variable as t. So these derivatives, this y prime, z prime, all these derivatives would be written in terms of t. Got it? So in that case, this d operator would be written as ddt. Next, we have d square operator. What is this? This d square is the operator, this kind of second derivative operator, and so on. We may have nth degree operator, and its representation would be this kind of representation. Got it? So this one, this y prime, y prime, y prime. What is this? Y prime is actually dy dt. dy dt. So this dy dt, what is this? This is actually ddt of y, and therefore we can write it as d of y in brief. D of y. Sometimes we apply this kind of bracket, sometimes we do not apply this kind of bracket. We simply write it d, that means the ddt operator operated on y. We could also write it in this way, ddt of y, just in order to stress that ddt is an operator, a derivative like operator, operating on the function y. We are uh, we are writing this bracket, but we can also remove this bracket, and removing this bracket we simply write it as y prime is equal to d of y. So similarly, if we have the second derivative y double prime is this kind of expression, d square dt square, this kind of d square dt square, and that is d square y. So similarly, if we have z prime and z double prime, over here we would have simply z, okay, and their z. So that is the notation about this kind of operator d, d square, d cube, p to the power of 4, and so on. And using this kind of operator, we can write this equation, this kind of differential equation in this form. We can write this expression as dy. This expression can be written as d square z. Similarly, we can write this second equation in this fashion. Say this is d of z. This is d square z. Okay. So this kind of notations are also used in our this will be used in our subsequent study. All right. Now, how to solve this kind of equation, differential equation? But let me show you what is the challenge of solving this kind of differential equation. You see, whenever you have algebraic equation, these are differential equations. Suppose we have two algebraic equations involving two variables. Suppose you have this kind of equation, maybe a1 or a0 x plus b, or maybe a1 y is equal to maybe rather we write it a01 or a11, a11, a12 is equal to maybe b1. And suppose we have this kind of equation, a21, a22 is equal to maybe b2. Then you know different techniques, method of elimination, cross multiplication, etc., etc., etc. You know different techniques of solving this kind of algebraic equation. This minded, these are not differential equations. Method of cross multiplication is there, method of elimination is there. Now, if you consider the method of elimination, what you do, you generally multiply this first equation by what? Maybe by, suppose if you want to eliminate y, then we can multiply this first equation by a22. If you want to eliminate y, then multiply the second equation by a12, and then from the resultant relation subtract the one relation from another. Ultimately you will get some expression uh, involving x. So in this way you will be able to find out the value of x, and whenever you get the expression or the value of x, then you can put it in one of these two equations and you will be able to find out the value of y. Okay. Now, if you want to apply the same technique in these two equations, got it? If you want to apply the same technique in these two equations, then how to apply that technique? Let us copy these two equations at first. So these are the equations, and these equations, we shall write these equations in this way, that say over here you see z is a dependent variable, and it may look a bit peculiar, but it is perfectly mathematically valid. We shall write it in this fashion. What we are doing, it may appear that as if we are taking this z common. So yes, you can consider for the time being, you can consider it as if we are taking this z common. And what is this expression inside the bracket? Is it a number? Answer is no. The expression within this bracket is not a number. This is actually an operator. And what is this? What is this operator? This is actually the operator b1 into this ddt. This capital D means this kind of operator. And what is d square? D square is equal to the second derivative operator. So this is the meaning of this total expression inside this bracket. Got it? So do not confuse this kind of expressions with numbers, purely numbers. These are not real numbers or complex numbers or any other kind of numbers. These are operators. So in operator, in case of operators, you will learn this kind of manipulation in future. That is, there is one theory or a part of mathematics that is called operator theory. Hmm, that is studied in mainly in master degree. So in operator theory, we generally write it in this way that the sum of this two, that is first operator plus second operator, that is operated on a dependent variable z. Okay, and that quantity, this mean the value of this total this term, that would be is equal to the this operator operated on z, the first operator operated on z plus the second operator operated on z. That's why it may look a bit peculiar, but it is perfectly mathematically valid that this operator is operated on z, and we write it with this kind of bracket notation. Got it? So this first equation, if we want to write them in terms of operator, then you see there is a z and this z is there. So what we do, we can write it in this fashion, like this, and then we can remove this z. Then we can write it in this way. So this is an operator, just a kind of operator, that a0 plus a2 into second degree second order derivative operator. This operator is operated on z plus a1 into ddt operator operated on y. Got it? So these are the two equations that we have. These are the simplified form of two system of linear differential equations. System of two linear differential equations. This is one linear differential equation and this is the second linear differential equation. Now suppose we want to eliminate one variable. Suppose we want to eliminate z. Then what to do? Just for the time being, consider these two quantities like some constant quantities or like some real number or complex number. Okay, for the time being, we can consider these two quantities as two numbers. Just in order to eliminate this z, then what we should do? Let me write it in this way. This is one differential equation and this is the second differential equation. Now, in order to eliminate z, what should we do? We can say that as if this is a number, then what we did in earlier case, we multiplied this first equation. We multiplied this first equation by what? By this kind of operator, and this second equation by this kind of operator. But over here you see we are not dealing with numbers. So although we can consider initially we can consider as the numbers, but what we are actually doing, we are as if we are multiplying some quantity. We are multiplying this equation by an operator. So operator, you see over here, if you look at this kind of operators, we write it d square y. That is actually the second derivative operator. And what is d square y? D square y is actually, you see this d square y. What is this d square y? This d square y is nothing but ddt of, what is this? This is ddt of y, isn't it? So this d square y is the derivative with respect to y, but 2 times derivative. Hmm. And that's why this expression can be written in this way: d operated on d of y. This dy dx, this is written as d of y. So this d square is nothing but as if we are multiplying d on dy, or we do not say multiplication, rather multiplication would be mathematically a wrong word. We would say we are operating this operating this d on this quantity d of y, and we will get d square y. Got it? So it behaves like multiplication, but it is actually a kind of operator. DDT operation is performed on this quantity. Clear? So over here, what we shall do, we shall write them on the left. Okay, like this, on the left. And over here as well, this expression will be written on the left, because operator is always written on the left. Let me minimize it a bit. Hopefully this is clear to you. Now you see, this expression and this expression, these are same expression. This expression and this expression, these are same expression. So now if we subtract them, if we simply subtract one equation from the second equation, what we shall get? We shall get this expression subtracting. We shall get this expression minus this expression. That is equal to this right hand side minus this right hand side. Okay. Now how to make these expressions a little simple expression, because you see this is actually a constant. A1 can be considered for the time being as a constant quantity. You know, if it is a constant quantity, we started with the fact that this A0, A1, these were initially functions of x. I told you that just for simplicity, I took I have written this kind of functions as simply A2 and all. But if further, if these are not functions, if A2, A0, A1 or B0, B1, B2, these are not functions, these are simply constants, then our computation becomes a little easy. I told you that our computation would be little easy whenever we deal only with this kind of constant coefficients. So if these coefficients are constant quantities, then you see what happens. You see over here, let me show you. Say d of a constant a0 or a1, whatever you call, say a1 of dy. What is d? Capital D means ddt operator. Okay, capital D means this ddt operator. So what we shall have? We shall have ddt of a1 into what is dy? Dy means dy dx. Capital D of y means this dy dx. Now, if this a1 is a constant quantity, we can write this expression. We can write this expression as if we are shifting this a1 outside this ddt operator, and then this expression ddt operated on d of y, that would be simply, that would be simply a1 into d operated on dy, that is actually a1 into d square y. Okay, so what I am trying to say is that whenever we have a constant term like a0 or a1 or a2, then we can shift this a0, a1, a2 outside this kind of derivative operators. Hmm? It may be this operator may be d square, d cube, or whatever it is. We can always shift all this kind of a0 or a1 or a2, this kind of coefficients outside this derivative here. And that's why over here in this term, you see, actually I should write it in this way, within a bracket. Again, this should also be written within a bracket. So now in the next line we can shift this operator, we can shift this constant outside this operator, and we can simply write it in this way. Similarly, over here this b0 can be shifted outside this, and we can simply write it in this fashion. And what is this? b1 d, b2 d square dy. Okay, b1 d. Let me write it in this way. Say over here, you see b1 d. b1 d means b1 d is operated on dy. Similarly, d squared is operated on dy. So b1 d, this d operator is operated on dy. So we will have actually d square y. And over here d square into d, that is actually d cube y. So third derivative of y appears. And over here as well over here, this y should be written over here and over here. So what we have, we actually get cubic expression, third order derivative of y. So apparently in this, if you look at this expression, what is that function? Yes, this is the differential equation. Apparently it looks that these are the differential equations and the highest degree is equal to 2. And highest degree may be 2, but if you look at this a little carefully, if you want to eliminate one variable, you will find that the highest degree is not 2. This is actually third order differential equation. Highest order is not equal to 2. The highest order may be much more higher than 2. Got it? So if you get higher order differential equation, solution of that kind of differential equation might be a bit complicated. So that is the problem in solving this kind of simultaneous linear differential equation. Today I am just stating about the problem, not the technique of solving that problem. Got it? And over here apparently it looks that we are multiplying by this kind of operator, but this is not a multiplication. Then what we say, we write it in this way: operation or operating the first equation by, what we are doing, as if we are multiplying the first equation by this kind of operator. So we do not call it multiplication, we rather call it operation. So we rather say operating the first equation by this operator, and second equation by which operator? By this kind of operator. So over here, please be very careful about this language. you make mistakes on this kind of languages. You generally write multiplying this first equation by this operator and the second equation by this operator and all. And frankly speaking, we the teachers do not expect from a student of honors course to make this kind of silly mistakes. Clear? So be very careful about this kind of techniques or terminologies. Today I am in this class, I am just demonstrating the problem of solving a system of linear differential equation. That is about the problem. In the next and subsequent classes, I shall show you the solution technique of this kind of simultaneous linear differential equation. So that's all for this lecture. Thank you for being with us.